All right, let's get started on 4.1. Okay, so 4.1 is about, in 4.1 through 4.3, we're going to be talking about analysis of functions. Our goal is to basically understand what the graphs of functions look like. So that involves us finding maximum and minimum values, periods or intervals of increase and decrease. It requires us to talk about concavity. So we're going to talk about cusps and vertical tangents and all kinds of stuff. So to get us started, let's talk about this first set of concepts: increase, decrease, and concavity. So this is the this is what we'll do in 4.1. So, so first of all, let's say that f is defined on an interval containing x1 and x2. We say that f is increasing on the interval if f of x1 is less than f of x2 whenever x1 is less than x2. And here's a picture of that, right? So x1 is less than x2 here, and notice that f of x1, the function value, is less than f of x2, okay? So in other words, you can kind of think of it like if you're riding this, like if this is a roller coaster and you're riding it from left to right, then you are climbing, right? You're increasing. So this is increasing. F is decreasing on the interval if f of x1 is greater than f of x2 whenever x1 is less than x2. So here we have x1, it's less than x2, but f of x1 is greater than f of x2, so it's decreasing, right? You're falling. If you imagine riding a roller coaster, then you're falling down the function. And then finally, f is constant if f of x1 equals f of x2. So if the function values are the same, right, then the function is constant. Here's another picture of this, right? So let's say that you had this kind of crazy looking function. This function would be increasing from here until we reach point A, and then it would be decreasing from point A to point B, and then it would be increasing again from point B to point C, and then from C on it looks like it's constant, right? So so that's what we mean when we say increasing, decreasing, constant functions. Now, what does this have to do with calculus? Well, so let f be a continuous function on some closed interval ab and differentiable on the open interval ab. If f prime of x is greater than x, so if the first derivative is positive for every x in the open interval from a to b, then f is increasing on the closed interval ab. Okay? Similarly, if the derivative is negative, then f is decreasing on that interval, right? So if the derivative is positive, then the function is increasing, right? If the derivative is negative, then the function is decreasing. And that makes sense. I mean, we've talked about derivatives in the past, and you know that the derivative is the slope of the tangent line. So if the slope of the tangent line is positive, then obviously the function is increasing, right? If it's negative, then obviously the function is decreasing. If the derivative equals 0, then f must be constant on that interval, right? Because there's no change. If the slope of the tangent line is 0, then there's no change occurring, right? You just have a flat, constant line. So let's practice applying that to these three functions here. So let's find the intervals on which the function is increasing and or decreasing. Okay, let's see. So we're going to do this for 3 examples. Let's do this for f of x equals x squared minus 4x plus 3. You could actually do this one without calculus because you know from your algebra days that this is a quadratic function, so it's a parabola, and that parabola is opening up because the leading coefficient's positive, which means it's gonna kind of look like a U shape, okay? And then it's going to be decreasing until it reaches its vertex, and then from its vertex on it's going to be increasing. So if you can find the vertex, then you can find where it's decreasing and where it's increasing. But let's see if we can do the same thing using calculus, okay? So using calculus, we would use that theorem we just talked about. We're going to calculate the derivative, and then figure out where the derivative is positive and where it's negative. That'll tell us where the function is increasing and where it's decreasing. So f prime of x is going to be 2x minus 4, right? And now we want to know where 2x minus 4 is positive and where 2x minus 4 is negative, right? So what we can do is set this equal to 0 and solve. So we're going to say 2x minus 4 equals 0. Implies that 2x equals 4, which implies that x equals 2. So f prime is equal to 0 right at x equals 2, and that's the only place where it equals 0. So everywhere else it's either positive or negative. And to test where it's positive and where it's negative, you could make a little sine chart, something like this, right? So you could say so you have stuff to the left of 2, that would be from negative infinity up to 2, right? And then you have stuff greater than 2, that would be from 2 to positive infinity. And then you could say something like, you know, sine of f prime or whatever on that interval, right? Okay. So on the interval from negative infinity to 2, right? If we plug in something like, say, 0 here, 2 times 0 is 0, 0 minus 4 is negative 4, so you get a negative on that interval. If you plug in something bigger than 2, like say 3, 2 times 3 is 6, and 6 minus 4 is 2. That's a positive number. Okay? So what does that tell you? That means, that tells you that f is decreasing here and increasing here. That may seem like a little bit of overkill for this particular function because this was kind of a simple one, but you'll see that sine charts, you know, come in handy for some of the other examples that we'll look at. So so there you go, right? We would say, well, okay, so we're decreasing from negative infinity to 2, and then increasing from 2 to infinity. And actually, I guess with the theorem that we looked at here, we actually said that it would be increasing and decreasing on these closed intervals. So really, you could close off the 2 and say it's decreasing from negative infinity to 2, including the 2, and increasing from 2 to infinity, including the 2. I don't love that, to be honest with you, but I'm because I think that at 2 itself, it's neither increasing nor decreasing, right? At 2 itself, that's where it changes from increasing to decreasing. So I don't love having the closed interval, but I think I'm following the convention of your book, right? So this is what the book is going to say. These are the answers that you would get in the back of the book. Okay, so that's that one. Let's look at another one. Okay, so the next one I want to look at is f of x equals x cubed. Okay, so this is another kind of simple one, I guess. And let's see. F prime of x is 3x squared. Now we want to set that equal to 0 and solve. So we'll say this implies that x squared equals 0, which implies that x equals 0. So that's the only possible place where this thing could change from increasing to decreasing. Well, so if we make a sine chart again, okay, so if we make a sine chart again, we have stuff to the left of 0 and then stuff to the right of 0. And if we plug in values here, like if I plug in, say, -2 to the derivative here, -2 squared would be a positive number, and a positive times a positive would still be positive. If I plug in a positive number here, like 5 squared is positive, and something positive times something positive is still positive. So we didn't change from increasing to decreasing at all. We're just increasing the entire time. So this entire function is increasing. So it's increasing on its entire domain, okay, from -infinity to +infinity. That's where this thing is increasing. It's increasing the whole time, okay? So so that's that. And that should coincide with what you know about what the cubic function looks like, right? X cubed looks like this. Well, it's just increasing the whole time, right? You do have this little point right here at 0 where something interesting is happening, but it's still increasing on its entire domain. Okay, let's look at one more. And this one, I'll let you pause the video and see if you can work this one out naturally, because it's the most complicated of the examples. Let's do f of x equals 3x plus 4 plus 4x cubed minus 12x squared plus 2. So go ahead and give the video a pause and see if you can figure that one out. Okay, here we go. Here's my solution anyway. F prime of x is going to be 12x squared, or sorry, 12x cubed plus 12x squared minus 24x. Okay, now we're going to set that equal to 0 and then solve for x. So I know I can factor out a 12 and an x. That would leave me with an x squared plus x minus 2. And then I can factor that a little further. And we can call this x plus 2 and x minus 1. Okay, so places where this could change from increasing to decreasing would be at 0, at -2, and at +1, right? We get, you know, x equals 0, or x equals -2, or x equals 1. So these are the possible places where the derivative could change from positive to negative, and therefore where the original function could change from increasing to decreasing. So let's make our sine chart. This time it'll be a little bit more interesting because we have a lot more places where things could change. So I've got to kind of put these in order. So this one would come first, right? -2. So the first interval I would look at would be -infinity to -2. And then the next interval that I would look at would go from -2 to 0. And then the one after that would go from 0 to 1. And then finally the one after that would go from 1 to infinity. So these are the 4 intervals that I'm going to look at. And let's look at the sign of f prime. So if I plug in a negative number, like if I plug in like -3, let's say. So if I plug in -3, and it's probably easier to plug it into the factored form down here, because then you can just quickly tell if it's positive or negative. So if I plug in a negative, I'm going to have a negative. So maybe I'll say this. It's going to be a negative times -3 plus 2 would still be negative times -3 minus 1 would still be negative. 3 negatives is going to make a negative. Okay? So it's going to be decreasing on that interval. If I plug in something between -2 and 0, like -1, let's see. This is going to be a negative. -1 plus 2 would be positive. -1 minus 1 would be negative. That's going to make a positive. So we're increasing here. Okay? If I plug in something between 0 and 1, that's a little more challenging. This is a 1/2, right? Then we're going to have a positive, and a negative, right? So it's going to be positive times negative. That'll make a negative. So we're decreasing. And then from 1 to infinity, so if I plug in like 2, it'll be positive, positive, and positive. That'll make a positive overall. So we're increasing on that interval. Okay, so I'm not going to bother rewriting my answer. This is my answer, right? We're decreasing from negative infinity to negative 2. We're increasing from negative 2 to 0, and so forth. So there's my answer to that particular problem set. Okay. So moving on. Related to the concept of increasing and decreasing in functions, right, is the concept of concavity. So here's how concavity works. So if f is differentiable on an open interval, then f is said to be concave up on the interval if f prime is increasing on that interval. F prime is increasing on that interval. So not f, but f prime, right? So f is concave up if f prime is increasing on that interval, and it's concave down if f prime is decreasing on that interval. And here's a picture to maybe help you understand the concept there, right? So let's say that you have this function, right? So this curve is supposed to represent the original function. Now, notice that if you look at the derivatives, right? In other words, the slope of the tangent line at arbitrary values along this curve. Like here, the derivative is this kind of steep function. Here, it's this sort of less steep function, but it's a negative slope, right? It's negative, and then it's less negative, and then it's less negative, and then it becomes positive, and then more positive, right? So the derivative is increasing, right? F prime is increasing the entire time. And so we call this kind of curve concave up. So a curve is concave up if its first derivative is increasing, okay? And then similarly, it's concave down if its first derivative is decreasing, right? So here the derivatives start really steep in the positive direction, then they become less steep, and then less steep, and then they become negative, and then they become more steep in the negative direction, right? So the derivatives are decreasing the whole time. So this is a concave down function. So graphically speaking, you can kind of remember this. Like if you look at the graph, then the graph is concave up if it holds water, and it's concave down if it spills water, right? So this if this were a cup, it would hold water just fine. This one would not, right? So concave up means that you hold water, concave down means you don't. But in terms of derivatives, it's concave up if the first derivative is increasing, and concave down if the first derivative is decreasing. Well, so if we treat the first derivative as like a function, and we apply the same facts that we were applying on this page about, well, when can you tell if a function is increasing? Sorry, when can you tell if a function is increasing and decreasing? It's, well, you take the derivative. So if you take the derivative of the derivative, and you get a positive second derivative, then that must mean that the first derivative is increasing, which means that the original function is concave up, right? And similarly, if you take the second derivative and the second derivative is negative, then that means the first derivative must be decreasing, and so the function is concave down, right? So that leads to this theorem, right? So let's say that f is a twice differentiable function on some open interval. If the second derivative is positive for every value of x in the open interval, then f is concave up on that interval. And then if the second derivative is negative on that interval, then f is concave down. Now, I should point out that functions usually aren't just strictly concave up or concave down. Usually, right, you can have situations like this where maybe, you're concave down until you reach like that point right there, and then it seems like you're concave up after that, right? Like if you imagine just this half of the graph, it looks concave down, you're spilling water. If you look at this half of the graph, then it looks like it's concave up, right? You hold water. And so this point right here, where you change from concave down to concave up, that's called an inflection point. Okay, that's an inflection point. And so that's what I'm saying here in this definition, right? So if f changes concavity at some point x naught, then the point x naught, f of x naught, is an inflection point of f. So this would be an inflection point. Okay, it's an inflection point of the original graph. Okay, so I want to run you through several examples. We'll determine where the function's increasing and decreasing, where it's concave up and concave down, and then we'll state what the inflection points are, if any. And we can verify our work by looking at a graph in Desmos. Okay, so let's go through these. I don't know if I want to rewrite all of those directions. You can pause the video and rewrite the directions, right? Determine where the function is increasing, decreasing, concave up and concave down, state the inflection points, and then we'll look at a graph, okay? So I'm not going to rewrite all of those, but let's look at the examples themselves. So we've got, for part A, f of x equals x cubed minus 3x squared plus 1. So let's determine where this is increasing and decreasing, where it's concave up and concave down, and we'll state its inflection points. So to determine where this function is increasing and decreasing, we need to take the first derivative. Okay? And then we'll set that equal to 0 to see where it could potentially change from increasing to decreasing. Okay? So I can factor out a 3x, right? I'm going to be left with x minus 2. Okay, so x equals 0 or x equals 2. Okay, so I'm going to make my little sine chart now. So my interval and then the sine of f prime. Okay, so on the interval from negative infinity to 0, if I plug in a test point in that interval, like negative 1, then I'm going to have a negative times a negative, and that will make a positive, right? A negative times a negative equals a positive. Okay, from 0 to 2, if I plug in a test point in that interval, say 1, right? Then I'm going to have a positive times a negative, and that's going to make a negative. And then finally, if I, on the interval from 2 to infinity, right, if I plug in a test point there, like 3, then I'm going to have a positive times a positive, and that's going to make a positive. So what does that tell me? That tells me that I'm increasing here and here, and I'm decreasing here, right? So I'm increasing from negative infinity to 0, but also from 2 to infinity, and I'm decreasing. Okay, I'm decreasing from 0 to 2. If you've never seen the union symbol, this just means, you know, this set and this set, like all of the solutions put together, I guess. I'm not sure if the book will even use this. It might just put a comma and say, well, I'm increasing here and here, right? Something like that. Okay, so that answers the first question. Now the second question is, where is this function, this original function in black ink, where is it concave up and where is it concave down? And to answer that question, we have to figure out where the first derivative is increasing and decreasing. Well, to figure out where the first derivative is increasing and decreasing, we need to take the second derivative, right? We need to take the derivative of the derivatives, right? So we're going to take f double prime. In this case, f double prime is going to be 6x minus 6, right? Okay, and then we do the same thing as we did before. We're going to set this equal to 0 and solve for x. I think we're going to get 6x equals 6, so x equals 1. So x equals 1 is the only place where f could change concavity, right? F might change concavity there. The only way to be sure is to do what we've done before, make a little sine chart. Not f of x, f double prime of x. Okay, So to the left of 1, if I plug in, say, 0, I'm going to get a negative value. To the right of 1, if I plug in, say, 2, I mean, 12 minus 6 is positive there, right? Okay, so what that tells me is that here I'm concave down, okay, because the derivative is negative, or the second derivative is negative on that interval, and here I'm concave up. And since I changed concavity at x equals 1, that means x equals 1 is an inflection point. To figure out the y coordinate of this inflection point, I need to plug this back into, now be careful, right? Because I've been plugging stuff into the second derivative. Here I plug stuff into the first derivative. But if I want to find the point that's actually on the graph of the original function I'm looking at, I need to plug this back into the actual function itself to figure out what its y value is. So my inflection point is the point 1 f of 1, not f prime of 1 or f double prime of 1. It's 1 f of 1, right? What's f of 1? If we plug in 1 here, we get 1 cubed minus 3 times 1 squared plus 1. So that's 1 minus 3, which is negative 2, plus 1, which is negative 1. So 1, negative 1 is the inflection point. Okay, and so there you go. We're increasing from negative infinity to 0, and from 2 to infinity. We're decreasing from 0 to 2. We're concave up from negative infinity to 1, and then, or sorry, concave down, and then concave up from 1 to infinity. Now I'm curious to look at this graph in Desmos to see, to kind of verify that what I came up with is correct. So let me put this in. F of x equals x cubed minus 3x squared plus 1. Okay, so sure enough, notice that that I am increasing from negative infinity to 0, and then I'm decreasing from 0 to 2, and then I'm increasing again from 2 to infinity, just like we thought. As far as concavity is concerned, we said that 1 was an inflection point. So at x equals 1, the point 1, negative 1, if I can get it on there, well, it's not going to let me for some reason, but there you go. That point right there is an inflection point. So notice that to the left of that point, I am concave down. To the right of that point, I'm concave up. Okay? In fact, I could just put, whoops, 1, negative 1 on the graph, right, to make it clear. Right, so concave down and then concave up. So yeah, that confirms all of my suspicions from the work that we did on that exercise together. So that's that one. Let's look at another one. Ooh, this is kind of an interesting one. Let's do f of x equals x times e to the negative x. Very interesting function, I would guess. So why don't you go ahead and give the video a pause and see if you can figure out where that function is increasing, decreasing, where it's concave up, concave down, state the inflection points, etc. Okay, so here I go. So first derivative, product rule, right? So I'm going to say derivative of the first times the second plus the first times the derivative of the second. Derivative of e to the x is e to the x, but because it's not just e to the x, it's e to some function, so I have to use chain rule there. So I'm going to say times the derivative of negative x, which would just be negative 1, right? I can clean that up a little bit. So that's e to the negative x times, I'm going to factor that out actually, and I would have 1 minus x left over, right? Now I want to set that equal to 0 and solve for x. So let's remind ourselves e to the x looks like this, right? It's an exponential function. E to the negative x would be a reflection across the y-axis, so it's going to look like that. But either way, it's never going to be 0, right? E to the negative x. It's like no matter what you plug in for x here, e to any power, it's never going to be 0, right? If you plug in a really large negative number, you're just going to get a really large positive number back. If you plug in a really large positive number, you're just going to get a really small positive number back. But you're never going to reach 0. So the only place where this derivative could be 0 is if x equals 1. Right? That's the only place where it could be 0. So, well, let's see. Let's see whether it's increasing or decreasing now. So, okay, so to the left of 1, if I plug in something like 0, I'm going to get e to the 0 is 1, so I'm going to get a positive number there. And then 1 minus 1 is, or 1 minus 0 is 1, so I'm going to positive there. Positive times positive is going to be positive. So it's positive on that interval, which means it's increasing on that interval. To the right of 1, if I plug in like 2, for example, e to the negative 2, that's just 1 over e to the positive 2, it's still a positive number. 1 minus 2 is negative 1, that's a negative number. A positive times a negative is going to be a negative, so it's decreasing there. Okay, so that does it for where the function is increasing and decreasing. Now let's see if we can figure out where it's concave up and concave down and find its inflection point and all that stuff. I'm going to try to squeeze this in over here. So let's take the second derivative, f double prime of x. I'd like to avoid using product rule. I'm not going to be able to avoid using, well, if I can't avoid using product rule, then I might as well just use this thing down here. So I'm going to say derivative of the first, which is going to be e to the negative x times negative 1. I'm just going to call that negative e to the negative x. Derivative of the first times the second, plus the first times the derivative of the second. Derivative of 1 minus x is just going to be negative 1. All those pesky negative ones. Well, there you go. I can do the same thing, though. I'm going to factor out e to the negative x. In fact, I'm just going to factor out a negative e to the negative x, since this is negative and this one's also negative, right? What would that leave me with? That would leave me with 1 minus x plus 1. Oh, be careful with the negatives there, right? But it's a negative... yeah, that's right. That's right. Okay. Okay, so this is negative e to the negative x times 2 minus x. Okay, so now the question is, where is this equal to 0? Again, negative e to the negative x is never going to be 0. Right? This was e to the negative x. Negative e to the negative x is going to be this function flipped over the y-axis, kind of like that. But it's never going to equal 0. So this doesn't equal 0. The only place this thing could be 0 is at x equals 2. So I can plug in something to the left of 2, something to the right of 2, and see where the function is negative and positive. So this is the second derivative now. Okay, so if I plug in something like 0, then I'm going to get e to the 0 is 1, but it's a negative 1, so I get something negative there. 2 minus 0 is positive 2, so a negative times a positive is a negative, so it's concave down on that interval. And then if I plug in something like 3, here I'm still going to get a negative number. Here I'm going to get a negative number. A negative times a negative is a positive, so it's concave up on that interval. That means that 2 is an inflection point. F of 2, which would be 2, and then if I plug in 2 here, I'm going to get 2 times e to the negative 2, or in other words, 2 over e squared. So 2 comma, I'll just leave it 2e to the negative 2. But there you go, there's your inflection point. You could plug that into your calculator to get a sense for how big that number is. But I'm going to look at a graph at this. I'm going to look at a graph of this anyway. So let's just go back to Desmos. So our original function f of x is xe to the negative x. Ooh, okay, very interesting looking curve. All right. So we said that we would be increasing from negative infinity to 1. And it does indeed look like that's the case. And then we're decreasing after that, and that again looks like that is in fact what's happening. As far as concavity is concerned, we said that we would be concave down from negative infinity to 2, and then concave up everywhere else. So that's kind of interesting, right? But yeah, definitely to the left of 2, that looks concave down, and to the right of 2, it looks slightly concave up, right? It's kind of maybe a little bit hard to tell, but it is concave up to the right of 2. So yeah, so that is the inflection point right there. Okay, how am I doing on time? Well, we've been at this for 36 minutes. We can do a couple more examples for sure. Let's do a couple more. Usually class would meet for 50 minutes, so we've got a good 15 minutes left before I start to feel bad about how long the video is. I don't feel bad yet. So we'll say f of x equals x plus 2 sine x. Now, again, we're finding intervals of increase, decrease, concavity, right, etc. And there's going to be a whole bunch of changes in concavity and stuff when you're dealing with like the sine function. So let's restrict ourselves to just look between 0 and 2 pi. Okay, so I'm not interested in like the entire domain of this function. I'm just interested in what's happening between 0 and 2 pi. Okay, because otherwise we would have infinitely many values that we'd have to take care of. So let's not do that. Let's save ourselves a little bit of effort and just look between 0 and 2 pi. So go ahead and give the video a pause. See if you can figure this one out. Okay, here's my solution. So to figure out where this is increasing and decreasing, take the first derivative as usual. It's going to be 1 plus 2 cosine x. I want to set that equal to 0 and then solve for x. So I'm going to get cosine x equals negative 1/2, right? And then so I know that cosine is equal to 1/2 when x is pi over 3 radians. However, we're looking at when cosine x is equal to negative 1/2. So that would mean that we must be in quadrant 2 and 3. If you're a little bit rusty on your trig, then you might need to review this stuff a little bit. But yeah, we should be in quadrant 2 or quadrant 3. You could take cosine inverse of both sides, of course. That'll get you the solution in quadrant 2, but it won't get you the solution in quadrant 3. So just be aware of the fact that there are going to be multiple solutions here. But anyway, but we should have, cosine pi over 3 is positive 1/2. So cosine of 2 pi over 3 should be negative 1/2, right? So 2 pi over 3 is one solution. And then the solution in quadrant 3 should be 4 pi over 3. Okay, so those are the two places where f could change from increasing to decreasing. The only way to be certain is to do what we've been doing, right? Make a little sine chart. So here we go. So let's go from, not, because we're only interested between 0 and 2 pi, right? So I'm going to go from 0 to 2 pi over 3. If I choose a value in there between 0 and 2 pi over 3, like pi over 3, I suppose, would be a good one. Right? If I plug in pi over 3, cosine of pi over 3 is positive. 2 times a positive number is positive. 1 plus that is still going to be positive. So we're definitely positive on that interval, which tells me that we are increasing here. Okay. If we plug in something between 2 pi over 3 and 4 pi over 3, that's a little more challenging. Well, maybe just pi. Let's plug in pi, right? So if we plug in, right, pi is in that interval. If we plug in pi, cosine of pi is negative 1. 2 times negative 1 is negative 2, and negative 2 plus 1 is negative 1, so we're negative here. That means the function is decreasing from 2 pi over 3 to 4 pi over 3. And then from 4 pi over 3 onward to 2 pi. Let's plug in something there. What would be a good one? Like 3 pi over 2 would be good. And if we plug in 3 pi over 2, cosine of 3 pi over 2 is 0. 2 times 0 is 0. 0 plus 1 is 1. That's a positive number. So we're increasing on that interval. Okay, very interesting. I'm really interested in looking at this function in Desmos here in a second, so I can verify that all this stuff is correct. But yeah, that's what we're getting. Okay, now for concavity. We take the second derivative. Second derivative here is going to be negative 2 sine x. And we want to know where that is equal to 0. Well, I know that sine is 0 at 0 radians and at pi radians. If I'm restricting my attention between 0 and 2 pi, those are the only, well, I guess if I say including 2 pi, then 2 pi also would be a solution. But anyway, this implies that x equals 0, pi, or 2 pi. Okay? Alright, but 0 and 2 pi are my endpoints anyway, so I don't really get, you know, a bunch of intervals. Really, the intervals that I'm looking at are the interval from 0 to pi, and then the interval from pi to 2 pi, right? So let's plug in some values to f double prime there. If I plug in something between 0 and pi, like pi over 2, sine of pi over 2 is 1. 1 times negative 2 is negative 2, so it's negative there, which tells me that we're concave down between 0 and pi. Then between pi and 2 pi, I could plug in something like 3 pi over 2. Sine of 3 pi over 2 is negative 1. Negative 1 times negative 2 is positive 2, which means I'm concave up on that interval. It also tells me that pi is an inflection point, right? So my inflection point is going to happen at pi and then f of pi. So that's pi, f of pi. If I plug in pi here, sine of pi is 0. 2 times 0 is 0, and 0 plus pi would just be pi. So you've got an inflection point at pi pi, which is kind of interesting. Let's take a look at this function. I can't resist. Okay, so let's say f of x equals x plus 2 sine x. Whoa, look at that thing. Okay, very cool. Alright, so we claimed we were really only interested between 0 and 2 pi, so in fact let me fix this so that so let's make the step pi. There we go. So we were only interested between 0 and 2 pi, right? So here to here, that little portion of the graph, we said that we would be increasing from 0 to 3 pi over 2. So I'm curious now. Let's see, x equals 3 pi over 2. Or I'm sorry, not 3 pi over 2, it was 2 pi over 3 is what we came up with, 2 pi over 3. That's that one. Ooh, yep, so we're increasing from 0 to there, and then decreasing from there to what I hope is 4 pi over 3. Yep, and then increasing again. Yeah, so that makes sense. What about the concavity? We said that we would be concave down from 0 to pi, right there. From 0 to pi, we're concave down. And then from pi to 2 pi, we're concave up. That seems to check out as well. Okay, so pretty cool. The very first example we looked at together in this section, how am I doing on time? Oh, I'm cutting it close now. So so I might call it there. I had one more example. Oh, I'll show you this last one because it's quick. But what I wanted to say is that the first example we looked at was just a parabola. It was simple. We could figure out where it was concave up and all this stuff without needing calculus. But see, for something like this, you've got to have calculus, right, in order to be able to do these kinds of problems. Anyway, the last one I want to show you is f of x equals x to the fourth. Let's see if we can hammer it out quickly. F prime is 4x cubed. If you set that equal to 0 and solve, then you're going to get x equals 0. That's the only possible solution. So if you want to know where this is increasing and decreasing, then you can plug in a test point, like -1. -1 cubed is -1 times 4 is negative, so you're going to be negative there. And then if you plug in something positive, like +1, you're going to get a positive. So you must be decreasing here and increasing here. Okay, and what about the second derivative? What about concavity, right? So f double prime is going to be 12x squared. If you set that equal to 0 and solve, then once again you're going to get x equals 0. So so maybe 0 is an inflection point. Let's see. Okay, so same interval, -infinity to 0. If I plug in something negative here, a negative squared is going to be positive, so it's going to be positive. And then on the other half, if I plug in like 1, 1 squared is positive times a positive is still positive. Okay, so notice that I'm concave up in both places. And that's the main reason that I wanted to show you this very last example. It's a really simple one, but it just goes to show you that, like, in all these other examples, the signs alternated. It was like pretty predictable, but that's not always the case. The signs aren't always going to alternate, so you have to be careful. And so in this case, since the concavity didn't change, we would say that there's no inflection point. Right? There's no inflection point here because the concavity did not change. Alright, so that's that. That was that last example. This looks just almost exactly like a parabola. You're welcome to look at it in Desmos to kind of convince yourself that there's no change in concavity, no inflection point. Okay, but that's all. That's all I wanted to say for this section. I think I've been talking long enough, right? 49 minutes.